Recall from a previous video where we discussed the fact that clear text passwords are not kept on the system because it would be easy for root or someone who had access as root to go in and read everybody's password. Instead, passwords are put through some sort of hashing function, a one-way hash, and then that information is stored in a file. In Linux, authentication information is kept in two files, as we discussed: the password file, PASSWD, which is located in the etc directory, and the shadow file, which contains the actual hashes. So let's take a look at the shadow file. Notice that I use sudo here, and as you see here, root is typically the first entry in the shadow file. Notice the exclamation point here. This means that root can't log in from the login screen, and all these other accounts in light blue are actually system services. Notice that they don't have a password. There's just an asterisk there. But if we get to the bottom, we see that we have user PC, which is me, and we see a long string of characters. Different hashing functions are used to create the hashes for passwords. For the last decade, the MD5 hash was used on most Linux systems. As you see here, notice there's $6. This indicates that a SHA 512-bit hash is being used for the hashing function. If you see a $1 sign there, that means it's an MD5 hash. So you see $1 here, you see the 6, you see another $sign. This right here is the actual salt that we discussed before, and then this is the actual hash, which includes both the salt and the actual password used. Recall from our last discussion that the reason we use a salt is that if two users have the same password, then this hash will always be the same, as is the case with all hashing functions. But if you have a randomly selected salt and you add that to the password, then this guarantees pretty much that this hash will always be different for users who even have the same password. So why do we conduct a password audit? The primary reason is to determine whether the users are complying with the password policy. For example, if it is required that users use 8 characters, which includes at least one alpha character uppercase and one alpha character lowercase and a number, then we need to make sure that they're actually following that policy. The only way we can do that is through password auditing. So how do we conduct a password audit? Well, we don't want to ask the users their passwords. What we want to do is we want to use software that performs an automated cracking function, which would generate hashes and then compare these hashes to this information in here, the hash, to determine whether users are actually using passwords in accordance with the password policy. And what we're going to do is that we're going to use a program called John the Ripper. And John the Ripper is a freely available password cracker that you can find on www.openwald.com/John. It comes in Linux and Unix versions as well as Windows and DOS. Since we're working with Linux, we're going to use the Linux version, which means that we're going to have to download the sources and compile them. There's only one issue that's going to keep us from using John the Ripper for conducting our password audit, and that is that John the Ripper does not support the hashing function that is used in Ubuntu 9.10 and above. And again, the hashing function that is used is the SHA 512-bit hashing function. So what I've done for the course is actually go in and made some changes to the software so that it now supports SHA 512-bit hashes, and therefore we will be able to use John the Ripper to try to perform a password audit on our users' passwords. So here's the source code for John, and I've changed the name here so it denotes that it supports 512-bit hashes. And then we can untar this with and what that did was it created a directory with all the files we need. Notice that we've got 3 directories here, and we have a README file. You should read that README file because it tells you how to use John. we go into the doc directory, we see it has a lot of information. It has examples that show you how to run John, and FAQ. It tells you how to install it, which essentially means that you're going to compile it. It has a file called modes that explains how the different modes work. And there's 3 modes, and we'll discuss those just shortly. Go back to the source directory, and we see that we have our source code here. Notice there's something that's called a make file, and this is required to compile the software. And just to show you simply how John works, and this isn't how all software is compiled. Sometimes you do it a little differently, but that's outside of the scope of this discussion. If you type make, this shows you all the different types of systems on which John can be compiled. So you have Linux x86 architecture, 64-bit. You have the same here, 32-bit. You can do it with FreeBSD or OpenBSD, Solaris, and even the Mac. If we scroll back up to the top, notice that this indicates that to compile John, we type make clean in the type of system. And the type of system I'm using here is a Linux x86 architecture 64-bit. So let's get out of this, and we're going to type make clean, and what clean does is it gets rid of those binary files, the the object files, the .o files we saw previously. So it's making, it's compiling from the beginning, and we type make Linux x86 64-bit. We type enter. Note that the GCC compiler comes pre-installed with Ubuntu. And that took, what, about 15 seconds. And so now we can go to the run directory. Let me clear this first so it's easier to view. The run directory. And we have our program, John. Notice that it's got several different other files. And if you'd like to know how to use John on your system, you can read the README file and the other files that are contained in the doc directory. But I've made it really easy for you because I've created a shadow file that has a number of passwords in it so that I can demonstrate for you how John works. Let's make this a little larger. And let's take a look at this file that I've created called Shadow2 for the demonstration. What I've done is I've taken the shadow file and I've extracted all the accounts that don't have passwords in it. Notice that we have 6 accounts. We have PC, Melanie, Suzanne, Philip, Kaylee, and Lindsay. Maybe that's only 5. Notice that each of these starts with a $6, indicating that these hashes are SHA-512 hashes. If you download the source code from the internet and you run John against this, it cannot calculate the appropriate hash, so it would never resolve to any of these hashes because John again does not support SHA-512-bit hashes. But the software that I've just installed does. So let's get out of this. Now we're going to demonstrate the 3 different modes in which John works. So the first cracking mode used by John, or actually by the user, is called single mode. And single mode uses information from the shadow file, such as usernames or any other relevant information that's included, for example phone numbers or anything like that. And then it adds mangling rules to this information, and the mangling rules will essentially take this user information and then add numbers before or after, or reverses the order of the usernames and uses those as the password. Because it's got a limited amount of information with which to work, it works very fast, but you see a lot of times that users will for example, if a user was named Sally, they may put or Sally 2010 as their password. The second is a dictionary attack. And a dictionary attack uses a word list such as a dictionary. It takes each of the words in the dictionary, adds the salt to it, and then hashes that, and then compares the resulting hash against the hashes in the shadow file. This takes longer, but it's more complete. The extent to which this is more complete depends upon which dictionary is used. For example, there is a dictionary that comes with every version of Linux, and it has about 9,000 words in it. But you can also use other dictionaries that are even more complete and add additional information. As we saw in one of the previous lectures, that we could use Chinese names or Russian names or names of cartoon characters or the names of famous baseball players, and this information wouldn't be included in your normal dictionary, but they could be used as passwords. One of the largest dictionaries that I've ever seen is something called the Argonne List, and it's a 24 megabyte file that's zipped, and it contains over 22 million words. So if you really want something that's exhaustive, this would be a good place to start. And finally, there's incremental mode. And incremental mode is a brute force technique, and we talked about that in a previous lecture. And so this goes through every possible password in the key space. And because this could actually run forever, we want to use this last if the other two don't work. And remember that you don't have to break everybody's password. What you want to see is if you apply reasonable force against the passwords that are used by your users and you don't break some of them, then that means that those that haven't been broken are probably good passwords. Those that have been broken, however, if they're broken especially with the single crack or the dictionary attack, must be changed. And so in order, we want to run the single attack, then the dictionary attack, and then finally the incremental. Let's see how we do this. So if we want some quick information about John obviously isn't in our path, so we got to type // to indicate that we want to run this file in our path, and we type John, and it gives some information on the cracking modes and information, for example, about showing the cracked passwords and so on. So we have single here, the single crack mode, which uses the usernames and other information in the shadow file and some heuristics to mangle the passwords. We have word list, which is a dictionary attack, and then we have an incremental mode. So let's clear this and let's run John in single crack, and we're going to apply this to the shadow 2 file. Okay, that was almost instantaneous. Notice that, like a lot of users, some users will use their username as their password. Some will add something very simple to the beginning or the end to create their password. So Lindsay's is Lindsay1. If we want to see what John is doing, we can hit enter, and it provides us some feedback. Notice it says that it had 2 guesses that were correct, how long it's been running, what percentage of the run is complete, the ciphers per second. It's trying 247 ciphers a second, and this is the key space that it's trying right now, and it's done. So that was probably, what, 15 seconds to run single crack, and we cracked 2 of the 6. Notice it was trying Kaylee 1918 as one of its passwords. Okay, that actually took 45 seconds. There it is right there. Okay, so now let's run, first of all we need to identify a dictionary. And the dictionary in Linux is in this directory, and it's called words. User shared DICT words. Let's take a look at what that looks like. And you see all it is a dictionary. It's got some names. If we go to the end, you see it even includes some special characters in here. If we want to see how big that dictionary is, we type word count "-L for the number of lines in that dictionary. It's got, oh, and I was wrong, it was 98,569 words in that dictionary. It's still not as big as Argon, which is 22 million. So now we're going to use John, and word list equals, so it identifies our dictionary, and then we type shadow 2. And notice that it's going to say that it's only loaded 4 password hashes with 4 different salts because it's already broken 2 of the 6. Hit enter, we see where it is, and this will take a while to complete, so I'm going to pause this video. And while it's cracking in the background, let's talk a little bit about some other password crackers and something called rainbow tables. And a rainbow table is a table of pre-computed hashes, and then these are stored somewhere in a file. And so instead of actually having to compute the hash, which is time intensive, all we need to do is to compare the hashes in the table to the hashes in the shadow file. And so since we're not computing anything, we're only matching, it's very fast. However, rainbow tables can be very large. For example, easily a large rainbow table could take up a terabyte. There's Windows crackers that are also available. For example, as we saw in a previous video, that Ophcrack is a very powerful Windows-based cracker. However, it's now commercial. You can still find the older versions of Ophcrack, and you can download those and compile that for your system. John the Ripper also works with NT and Landman hashes, so you could use that. There's a program called Ophcrack, which is freely available, and you can either install it to your system or you can run it off a CD drive. And Ophcrack uses rainbow tables. And also there's a very powerful program called Cain, or Cain Enable, which also runs on Windows and is able to do a lot more than John the Ripper, because it can actually extract passwords over a wireless network or passwords going over a network connection. Now remember, when we're using these under the authority of an organization which has asked you, as part of your job, to audit password usage. That is, making sure that users are complying with the password policies. It's very important that you have this written down somewhere as part of your job, and you get authorization from management to do this, because you can get in a lot of trouble if you don't. And there's a great illustration of this. It's someone in Texas, and I believe he was a consultant for Intel, came in and was asked to do a security audit, and he came in and he broke a lot of the employees' passwords using a password cracker. And when management found out about it, they actually had him arrested. I'm not sure why they did that, because they were asking for a security audit. However, what he should have done is get that in writing and make sure there was a clear understanding that one of the tasks that was part of the security audit and the password audit was to try to crack the user's passwords. Remember, even though these seem like they may be used by the black hats, that actually these are used for the purposes of ensuring that users are complying with security policies. Here is Ophcrack. As you see here, that you can load the passwords. You can either load a single hash, an encrypted or local SAM file, that's the security access module file, which holds the passwords in Windows, or a SAM off a remote system. You can also open a PWDump file, and PWDump is an application. It's a small DOS application that goes out and extracts password hashes, the NT and the Landman, from SAM files. And notice here that you can install the different rainbow tables. You would obviously have to download those and install those. and this is Cain, and I've used this for to show you what it looks like. Is that we can actually use this to sniff over a network connection, sniffing for passwords, and if this is done, then Cain will extract those passwords and then start to crack those. The sniffer is a program which puts the network interface card in something called promiscuous mode, which means that it's listening for every message that's coming to any particular IP address on the local network segment. These are all the different password hashes that are supported by Cain. PWL files are the old files used with Windows 95 and 98 and ME. The LM, the LANman, and the NT LANman hashes obviously are used in the Windows NT based Windows. Notice that it does Cisco MD5 hashes, and it even does VNC triple DAS. It does ND2, 4, and 5 hashes. It does SHA-1 and SHA-2 hashes. Right now, this is one of the government standards, the SHA-1 hash, which is anywhere from 128 to 256-bit hashes. But again, the one that Linux, especially Ubuntu, and its derivatives are now using is the SHA 512-bit hash. And you go down and even says it includes some wireless password hashing in here, as well as some database hashing. And I went back and I changed this because it's Ophcrack, O-P-H-crack. There was no T in there, so that's the correct spelling. So let's jump back here, and it's timed out. Let's see where we are. We're 39% through our dictionary, and I'm not sure why, but this seems to be running much slower than it used to, and I don't know if it's because of the changes that I made in the files before they were compiled. But it seems to, if I recall correctly, this used to be about 8 times faster than it is right now. It's doing about 250 ciphers a second, and I believe it used to be around 1600, but maybe my memory's not serving me correctly. Notice it's 60% complete. I'm going to pause this. While we're waiting for John to run through that dictionary, let's take a look at what I've been running on another computer. Is that I've been running John in incremental mode. Once again, that's the brute force mode. And you notice that on occasion that I would hit enter and I would see the space in which it was working. And you notice at about an hour and 55 minutes that through brute force that it found Kaylee's password, 12345. So now we've got 3 of the 5 passwords. We've got Kaylee's, which is 12345. We've got Suzanne's, which was her username. We've got Lindsay's, which was Lindsay1. Let's go back over here and see how we're doing. We got Philip's password, which was password. Now we're waiting on one more password, which was Melanie's password. At 21 minutes, 86% complete. We're in the S's of the dictionary. And there's our final password, sugar. And so we have 5 of the passwords we've broken. We have Suzanne, which was her username, Lindsay, Lindsay1, Melanie, sugar, Philip, password, Kaylee12345. Notice that these passwords violate good password policy. And it will be your job. You notice that these passwords in general are not following good password policy procedures. For example, using your username as your password is not a good idea. Just appending something simple to your username is not a good idea. Notice that these are 1, 2, 3, 4, 5, 6, 7 characters long, but essentially the longer your password, as we discussed in the previous video, the larger the password space and the more difficult it is to crack. The longest password we have here is password, which just happens to be 8 characters, which is getting to be a fairly long password. However, it's something that's very easy to guess and to crack because it's a dictionary word. Sugar's a dictionary word. And 1, 2, 3, 4, 5 is only 5 characters. And as you saw, that the incremental search found that fairly quickly. And so this ends this demonstration.